Actually, does this work?
No.
So if I tap the microphone, it seems to do something, but I think the audio on this microphone is very low. So I guess if I hold it up and talk like this, I can hear it okay? Alright, let's try it. Thank you. Okay, so for all of these applications, I think machine learning is our best technique for building all of these applications, but there's a lot of work to get algorithms to work, and each of those lines is easily anywhere from 6 months to 2 years of work for anywhere from half a dozen to 50 engineers. So is there a way to make learning algorithms easier to use and also make them perform better? In this talk, I'm going to illustrate most of these ideas using images and images to start because it's easier to talk about. But the ideas are general and also apply to other topics. And towards the end, I'll say a little bit about natural language and text as well. So, why is it hard for a computer to look at this image and figure out what it is? It seems so obvious what that is. How could a computer possibly fail to figure that out? Zooming into a small part of the image, where the little red square is, where you and I see a motorcycle, the computer sees this. Pixel intensity values. So the computer vision problem is to look at all those numbers and to say that those numbers represent the exhaust pipe or the motorcycle. It seems like a very hard problem to do that. In the machine learning world, where guys like me talk about machine learning, we usually say, we'll take the data, take the image, feed it to the learning algorithm, and let the learning algorithm figure it out. But this isn't how learning algorithms actually work in practice. So this actually doesn't work that well for most time. To explain why, let's pick a couple pixel locations, and I'm going to plot that image on this chart, where that image has a relatively dark pixel 1 and a relatively bright pixel 2, and so that motorcycle image appears at that position on the plot. Let's do this for a different motorcycle image. There's a bright pixel 1 and a dark pixel 2, so it appears to the lower right. And if I do this for a couple of non-motorcycle images as well, I may get that. If I do this for more positive and negative examples, for more motorcycle and non-motorcycle images, what I might get is a lot of examples that are very jumbled together. And if you feed this as data to your learning algorithm, it's very difficult for your learning algorithm to figure out what is and what isn't a motorcycle. So what is actually done in computer vision is, rather than feed the raw pixels to the algorithm, we usually instead try to come up with an intermediate representation known as a feature representation, and it is that which we feed to the algorithm. In this illustrative example, if we could write a piece of software to tell us whether or not an image has wheels in it, and if we could write a piece of software to tell us whether or not an image has handlebars in it, then your data set would look much more like what's on the lower right-hand corner. And it then becomes much easier for the algorithm to separate out the positive examples and the negative examples, to distinguish what is and what isn't a motorcycle. But the story doesn't end there, because we don't actually know how to write software to tell us whether or not there are wheels or whether there are handlebars in the image. So what is actually done in computer vision is people write software, very complex, opaque pieces of software, to try to capture vague statistical properties in the image. And so, say more about that in a little bit. But so this idea of computing features is pervasive in machine learning, where for images, you have to come up with vision features, for audio, you have to come up with audio features, and for text, you have to come up with natural language features. Given that the feature representation is the primary lens, or the primary prism through which our algorithm sees the whole world, it gives the feature representation a certain importance, and you have to ask where do these features come from. So in computer vision, the state-of-the-art answer for where you get features from is there have been teams of tens or hundreds or thousands of computer vision researchers that have spent decades, large fractions of their lives, and engineering vision features. The image on the upper left, SIFT, S-I-F-T, that's a screenshot I grabbed from the SIFT paper which is the most widely cited paper in computer vision in the last 15 years. And this is one piece of software for computing features for computer vision. I know the author, friends with the author, David Lowe, and it took David literally 10 years to come up with the SIFT algorithm. And I've read the SIFT paper maybe 5 or 6 times by now. And to this day, I still have no idea what the algorithm is doing. And the reason is, David Lowe had taken 10 years to fiddle with the pseudocode, to move pieces of code around, change parameters around, until 10 years later, he wound up with this very complex piece of software that computes very useful features, but it's very difficult to understand what it's doing. And that's how you get the best features for vision. How about audio? How do you find features for audio processing? Same thing. Teams of tens, hundreds, or thousands of audio researchers have engineering features for decades. And so the MFCCs, that's a very useful feature that we gave, after reading the MFCC papers many years, I'm still not entirely sure what it's doing. And how about natural language? Same thing, right? In fact, a lot of natural language processing research today is unapologetically about trying to find better features. So think about parsers. Why is there so much work writing better parsers? I don't actually care where the noun phrase is in my sentence. I don't actually do the piece of software to tell me that. But the reason we spend so much time working on better parsers is in the hope that the parser can generate useful features for me to then improve the performance of some downstream application, like web search, anti-scam, or machine translation that I actually care about. So coming with features is difficult, time-consuming, requires expert knowledge. And if you walk around the technology industry today, if you walk around Silicon Valley, or if you walk around the Beijing tech industry, most of doing applied machine learning research today is sitting around trying to hand design better features to feed to your application. So, can we do better? The next piece of what I want to talk about was from biological motivation. And it was really, there's this fascinating hypothesis that most of human perception, most of how we understand images, audio, text as humans, most of it may be due to not many different hand-engineered algorithms, but rather due to one single algorithm. And perhaps like many of you, I tend to treat biological inspiration with a great deal of caution and even a healthy dose of skepticism. But there's this fascinating hypothesis that most of human perception, most of how we understand data, may be due to one learning algorithm. And I think this gives us a hope that if we can find an approximation to this algorithm and implement it in a computer, that might be a much better way to make progress on computer data understanding, on computer perception. So let me share with you what this hypothesis really means and some evidence for it. Shown on the figure, that red piece of brain tissue is your auditory cortex, and you use it to understand sound. Neuroscientists have done the following fascinating experiments where they cut the wire in an animal between the ear and the auditory cortex and rewire the signal from the eyes, from the optic nerve, so that it eventually gets routed to the auditory cortex. It turns out if you do this, the auditory cortex will learn to see. And this is the word see in every single sense of how I know how to use the word see. These are animals that can do visual tasks, visual discrimination tasks. You look at images and make correct decisions, and they're doing it using that red piece of brain tissue. In this figure, that red piece of brain tissue is your somatosensory cortex, used to process touch. If you do a similar neural rewiring experiment, your somatosensory cortex will learn to see. So it turns out there's a wealth of evidence like this that suggests that depending on what data you feed the same piece of brain tissue, whether you feed it sight or sound or touch data, the same physical piece of brain tissue is able to process sight or sound or touch or language or other things. And in the same piece of brain tissue can process sight or sound or touch, then maybe there's one underlying algorithm that can process sight or sound or touch. just depending on what data you feed it. And it can discover the approximation to these algorithms and implement it. That will allow us to make a lot of progress in machine learning. It turns out that the hypothesis, this one learning algorithm hypothesis, has lots of other evidence. Just to run through this quickly, shown on the upper left is a system that's being developed to help blind people see. The way it works is you strap a camera to your forehead, a low resolution, strap a camera to your forehead of a blind person to take a picture of what's in front of you. You then run a wire to a grid of electrodes that you place in your tongue. You map a grayscale image to a pattern of voltage values on your tongue, where say a bright pixel maps to a high voltage and a dark pixel maps to a low voltage. And in 10 or 20 minutes, if you wear the system, you will learn to see with your tongue. There are also schools today training blind children to use echolocation and sonar, where you have children snap their fingers and they learn to interpret the pattern of sounds bouncing off your garments as sonar, so that you can walk around just snapping their fingers and never run into anything. Haptic belt. I have one of these in my lab. You wear a belt with a ring of buzzers around your waist and program it so that the buzzer facing north buzzes. So that's north, a buzzer here will buzz. And if I turn like this, that's north, and the buzzer here will buzz. And it turns out that just as you know where your hands are, where your arms are, even with your eyes closed, if you wear a haptic belt, which I have, in 5 or 10 minutes, you just know where north is. In the same way that I know where my arms are, even with my eyes closed. Wearing this for a few minutes, you just know where north is. It's in the same way. And finally, you can plug a third eye into the frog. So to surprisingly large extent, it's almost as if you can plug almost any sensor into almost any kind of brain, and the brain will learn appropriate representation or feature representation for whatever data you feed it. So the question is, can we get a computer to also learn appropriate feature representations automatically for whatever data you feed it? So here's the mathematical formalism of the problem. Given a 14 by 14 image hash X, you can represent the image hash using 196 row numbers with pixel intensity values. So the mathematical problem is, given that image hash, can you find a better representation, meaning can you find a better list of numbers, better feature vector, with which to represent that image hash other than just writing down the pixel intensity values? In order to do this, I'm going to turn one last time to biological motivation. So it turns out that in your brain and mine, when you see an image, the first thing your brain does is look for edges in the image. So an edge is a light region, like this, adjacent to a dark region, like this. So in your brain right now, there is probably a neuron looking for a 45-degree line or a 45-degree edge, like that shown here. And in your brain right now, there's probably a different neuron that is looking out for a vertical line or a vertical edge like this. So out of this knowledge, one thing we could do is to try to connect this. But I think it's more interesting, instead of trying to hand engineer something like this, to see if we can come up with algorithms to build this automatically. I started working on deep learning when I learned about this fascinating result of an algorithm called source coding by 2 neuroscientists, Olshausen and Deap. Olshausen and Deap are neuroscientists, and when they came up with this fast coding algorithm, they had published this result as a scientific critique to explain early visual processing in the brain. But when they published this paper, it was sort of like a mathematical result, like a basic neuroscience result, like an observation on the mathematics behind perception. And they had never envisioned that this would be used as a machine learning algorithm. But it turns out to be an unsupervised learning algorithm, meaning an algorithm that just learns from unlabeled data, and it gives a very good explanation for early visual processing. So let me explain the algorithm. Sparse coding takes as inputs m images, so x1 through xm, each of which is, say, a 14 by 14 image hash, so rn by n. And what it does is it learns a dictionary of basis functions, I1 through 5k, let's say 64 basis functions. And it learns it so that each of your input examples x can be approximately decomposed as a weighted sum, or as a linear combination of your 64 basis functions, and subject to the constraint that those weights, that those coefficients, aj, are mostly zero. Okay? The constraint that the aj's are mostly zero is called a sparsity constraint. Hence the name sparse coding. So, I think this is the only equation I have in this talk. So, I hope you enjoyed it. But to explain the same thing in pictures, when you feed a set of natural images to sparse coding, what it will do is learn a set of 64 basis functions, shown in this example by the 64 image patches on the upper right. Given a new test image, what it will do is select out a small subset, let's say 3 out of 64 of my basis functions, and explain my test example as a weighted sum, as a weighted linear combination of, say, just 3 of these 64 basis functions. So, a couple observations. First, sparse coding could have chosen absolutely anything it wants for these basis functions on the upper left. It's completely unconstrained. It can choose any basis function it wants. But it turns out, every time you want to run sparse coding, 100 times out of 100 times, the basis functions will all look like what you see there. They'll look a lot like edge detectors. In other words, sparse coding has, quote, invented edge detection. Second, in this example, what sparse coding is saying is that this image x is 0.8 times edge number 36 plus 0.3 times edge number 42 plus 0.5 times edge number 63. So if you represent the image by that list of numbers, A1 through A64, corresponding to the coefficients, the weights, those 64 coefficients, most of which are 0, then that list of numbers, A1 through A64, gives you a better representation of the image. It gives you a higher level, more succinct, more compact representation of the image. And in particular, that list of numbers tells you what edges appear in the image, and this is a more useful representation. It's better to know where the edges are in the image than to know where the pixels are. So from unlabeled data, there's going to be a higher level representation. Here, just a couple more examples. But just to summarize, sparse coding invents edge detection and it automatically learns to represent the image in terms of the images that appear. Other neuroscientists have also compared the edge detectors found by sparse coding and showed that it is quantitatively quite similar, not identical, fairly similar to the edge detectors observed in the primary visual cortex in the biological brain. Sparse coding gives by no means a perfect explanation, but a decent explanation of early visual processing. And it gives a set of features that are more useful for vision. So that was vision. How about audio? Emily Smith, who was a postdoc in Stanford, ran the following fascinating experiment. She took sparse coding and she applied it to audio data, and sparse coding learned these 20 basis functions. So this is a grid of 5 by 4, so 20 basis functions. So sparse coding had learned to explain audio clips as weighted sums of these 20 basis functions. What he did was, for each of these 20 basis functions, he went to a database of CAT, of biological auditory processing. And for each of these 20 basis functions, he found the closest match in the auditory processing system of a cat. So shown in blue are the output basis functions learned by sparse coding, and the closest matches in biology are shown overlaid in red. So the same algorithm, same piece of software, on one hand gives a very good explanation for early visual processing, and it also gives a decent explanation for early auditory processing. I'm not going to show the slide because of time And some of my students at Stanford have applied this to explain early touch processing, early somatosensory processing. And it turns out the same algorithm gives not a perfect explanation, but a surprisingly good explanation of the model of early somatosensory processing as well. So beyond sparse coding, what we can do is then recursively apply this idea to build even higher levels of representation. So the way we implement sparse coding is actually with a model called an artificial neural network. I'm not going to go into details, but loosely, it's a loose simulation of neurons in the brain where each of the basis functions, the 64 basis functions for images, or each of the 20 basis functions for audio, corresponds to a loose simulation of one neuron in an artificial brain biology. So each neuron in the brain is like a feature detector that's looking to find a specific edge or listening for a specific audio, a snippet of audio will happen. So with one layer of sparse coding, we can go from the image input pixels to one layer of simulated neurons on top that are edge detectors in the case of images. And what we can do is recursively apply this idea to build even higher and higher layers of representation. So let me show you what this looks like when you do this. When you apply one layer of sparse coding, you can group together pixels to form edge detectors. So what this visualization means is that this little square here, that visualization means that one of my feature detectors, one of my basis functions, or one of my little simulated neurons in my neural network has learned to detect vertical edges that look like that. If you recursively apply this algorithm, you can then learn to group together edges to form models of object parts, and then group together object parts to form more complete models of objects. These results were generated by training the algorithm on the dataset that comprised entirely of pictures of faces. And so on the second layer, this visualization means I have a neuron that has learned to detect eyes that look like that. And on the highest layer, this neuron has learned to detect faces that look like that. Okay? A couple technical details. Although not shown here, the highest level neurons actually look at much larger regions of the image than the lower levels of the neurons. So as you go up, each of these neurons look at bigger regions of the image. And because of the way of visualization, this isn't clear, but each of these neurons is actually computing a very complex non-linear function of the image. It's just that we visualize what the neurons look like. But the multiple layers of sparse coding actually are feature detectors that become increasingly complex non-linear functions of the image as you go up this hierarchy. So, training on the unlabeled data, we can learn very rich feature detectors. We learn feature detectors to look for faces in other objects. So what is a good thing? Well, here's some machine learning applications. Suppose you want to go back to the original problem and write a piece of software to recognize motorcycles, with which to learn to classify what objects are, with which to learn to classify motorcycles versus non-motorcycles. So one of the first data sets we looked at that we ran this on was a video activity recognition benchmark called Hollywood 2 benchmark. This is one of the hardest benchmarks in computer vision, where the task is to watch a short video clip and decide whether or not the video clip contained two people kissing, two people hugging, someone dragging, someone eating, to recognize activities in videos. Over the last few years, researchers in computer vision have hand-engineered and tried a lot of different features and made progress from like 38% up to 46, 47% accuracy. One of my students at Stanford decided that instead of hand-engineering the features, he would just have to learn them. And immediately, he was able to substantially outperform the previous data analysis. More broadly, for application after application, in audio, images, video, natural language, deep learning algorithms, these sorts of algorithms for learning features, have been knocking over the benchmarks very rapidly. In my entire professional life working in machine learning, I have never before seen any one technology knock over this many benchmarks this rapidly. this is just a few examples. Many research groups, really not just mine, but many research groups have been using these technologies to help with the benchmarks. And I should say, right here in Beijing, one of the leading groups in deep learning is in Baidu, where UCai leads the deep learning team that has done. I don't get that permission to talk about what products and applications it works on. UCai, Baidu really is one of the leading groups in deep learning and has developed tons of benchmarks and is making Baidu products that you're probably using for other objects. So, after getting to the stage that I showed you on the last slide, about 2.5 years ago, I sat down with my students and we spent a lot of time thinking through the question of how do you build a high accuracy learning system? Given where we are with deep learning technology, how do you take it to the next level? And for inspiration, we started looking back in the history of machine learning. We actually look back to around 2000, 2001, when most people were doing supervised learning, so learning from labeled data, and back in the day, back in 2000, 2001, the debates were on, given the leading learning algorithms of the day, these algorithms went up as on 90 days, what is the best algorithm? So my thinking has been heavily influenced by a study done by Banco and Rowe in 2001, where they took the leading learning algorithms of the day, supervised learning algorithms, and they ran a study comparing the effects of running different algorithms on different amounts of data. And their results is shown on the upper right, where the 4 different lines correspond to 4 of your leading learning algorithms of the day. And the result is very clear, right? As you give the algorithms more data, the performance goes up. And very often, a supposedly superior algorithm will outperform a supposedly inferior algorithm. A supposedly inferior algorithm will outperform a supposedly superior algorithm if you can give the supposedly inferior algorithm more data, just scale it up to bigger data set. And so results like these have led to a saying in machine learning that often is not who has the best algorithms, is who has the most data. So this is a result in supervised learning where data was really limited because there's a lot of words and labeled data. How about algorithms like sparse coding where you can learn from unlabeled data? With unsupervised feature learning, with algorithms like sparse coding, we can learn from unlabeled data. So all of us have access to an infinite source of data. Suck down as much data as you want off the web. And so it's no longer who has the most data that wins, it's who has the most computers. So who has the computational capability to process the essentially infinite amounts of data that all of us have. So one of my students, Adam Coates, ran an experiment in which he took the leading learning algorithms, the leading unsupervised feature learning algorithms of the day, and show them in different lines. And the trends here are made very clear, where the algorithm matters a bit, but it's really the bigger you can scale these algorithms, the larger you can scale these models, as shown on the x-axis, the better the performance. So given these results, we spent a lot of time thinking through how can we take the unsupervised learning algorithms, the sparse coding, the deep learning algorithms, and what will it take to build really large-scale versions of these models. So spend some time in Silicon Valley. I spent some time wandering around Silicon Valley trying to figure out where can I get access to a lot of computers in order to build really large deep learning algorithms. And I guess in order to explain what we did on building very large deep learning algorithms, I'm going to break the next part into 2 pieces. It turns out that when guys like me give talks on deep learning often combines labeled data and unlabeled data, where we use unlabeled data to learn the feature representation, and then we combine that with some labeled data to come up with the classification predictions. Does this work? Alright, so it works about the same story. So it turns out when you hear people give talks on deep learning, very often the supervised learning or labeled data and the unsupervised learning, unlabeled data results are often conflated. And it makes a very, sometimes makes the talk sound better, but it makes the results very confusing. So I'm going to deliberately separate out these two things and talk about applications where the performance comes from being able to exploit having lots of labeled data, and then later talk about results where the performance comes from being able to exploit a lot of unlabeled data. I'm going to start with learning from labeled data. And so what we did was we developed and so in 2011 I started a project at Google to take advantage of Google's distributed network infrastructure to build very, very large neural networks, to build these deep learning algorithms, starting with exploiting labeled data. So, given a neural network like that, like one of the network models that you saw, what we would do is take the model and partition it so that different parts of the model can live on different machines. And if you do that, then because the number of network connections we're cutting across is relatively small, there's some amount of communication that needs to take place across the different machines, but not an excessive amount. Within each machine, we then further exploit multi-core parallelism. Each of the machines has 16 cores or something. Then we can further exploit multi-core parallelism within a single machine to speed up the algorithms. So, with this form of parallelism, we did the learning using stochastic gradient descent or mean match stochastic gradient descent for those of you that know that. And it allowed us to parallelize our models across on the order of 100 machines, so maybe 1,600 cores. But then this still wasn't good enough for us. We wanted to layer on another layer of parallelism, where we don't just take a single model and distribute it mathematically as one stochastic gradient descent step. We does some learning to compute some update delta p that it wants to implement in the parameters. And then the parameter server will take the delta p from my model and add it to the global copy of the parameters. And then it will transfer p prime, get a new update, and sum it up again. This is how we're going to see this happen. And what this allows us to do is make multiple copies of this model workers with each of those copies of the model comprising maybe 100 machines. And each of my model workers at the bottom will proceed in parallel. With each of my 3 copies at the bottom will work on a different frontier. And I've built this here as though we have 3 model workers. In practice, we have anywhere from 10 to 50 model workers. And so, from an engineering standpoint, one huge advantage of using this parameter server setup is that if one of my slave models, if one of these 3 pieces at the bottom goes down, the rest of the model can keep on running. So it turns out that with our computers, the mean time to failure of the desktop computers maybe 3 years. Computer fails on average every 3 years. What that means is if you run on 1,000 machines, 3 years is about 1,000 days, right? So what that means is if you run on 1,000 machines, you have about 1 machine fail every day. Because of preemption and other problems, we actually have machines fail much more often than 1 day. But with this sort of architecture, if one of the machines is very slow because something goes wrong, because with 1,000 machines, there's just much higher variance in response times in the machines. If one of the machines goes down, or one of the shards goes down, or one machine is very slow and times out, we can just discard that shard, and the rest of the computer, the rest of the cluster, keep on making forward progress. When you work on thousands of machines, one of the issues you have to deal with is just the high variance. Some machines will just respond much faster than others because of weird things to do with the router or the memory or some machines like that. And this architecture makes us much more robust. And so, using this model, we are able to do 2 things. The first and more interesting thing to do is to train very large models. With 100 machines, by taking one model and spreading one model across 100 machines, we can train models that don't even fit in the memory of a single computer. So we train massive models. The second thing it does is even when we train very small models, it allows us to run much more quickly. So here we did a comparison with training on a cluster versus training on a single GPU. So for only very small models, we could fit in a GPU, that was possible to do. And we found that even compared to GPU training, by distributing our machine, by distributing our model across 10,000 cores, we can substantially train much faster than it's possible. But even more interesting is the fact that by distributing these models on so many machines, we can train models that don't even fit in a single machine. They certainly don't fit in a single machine. So, let's see. So what is this useful? What is this useful for? Again, we're going to separate out the results from what we did on supervised learning on labeled data from what we did on unlabeled data and unsupervised learning. So, I'm actually curious, how many of you use an Android cell phone? So, if you use the Android cell phone speech recognition, it's actually built on top of this deep learning architecture that MIT built. To give credit where it's due, just read the work of Vincent and part of the speech team at Google. But working with my team and building on top of this architecture, Vincent and Hu's team was able to substantially reduce the word error rate of the Google speech recognition systems. Over 20% error reduction in the error rate. It's a massive amounts of data. Other applications is also used in Google Street View.
哇塞，你看，电锯马呀！
And then there's a bunch of other applications.
哦，这是识别那个路牌，对。
识牌啊，这个。
他这个都能做，那些不是，更小太多了。
So we had a hypothesis that it will learn feature detectors. These individual neurons will learn to detect different features, and some of the feature detectors we hypothesized will learn to detect common objects in YouTube. So faces occur commonly in YouTube, and we looked at the neurons and we found that, lo and behold, one of the neurons was a face detector. So these are the neurons, these are the images to which one particular neuron responded the most strongly, shown on the left, and shown on the right is the input that most strongly activates this neuron. So we really have a feature that was a face detector. And we also documented that this face detector, is fairly invariant to rotations, contributions, so faces occur commonly in YouTube, so that we found a feature detector for that. What else do you think occurs commonly in YouTube? Cats. And we looked and we found that, lo and behold, we found a different feature detector that had learned to detect cat faces. The remarkable thing about this was no one had ever told it what a cat is. They had invented the concept of a cat by themselves. Now, detecting cats is a useful technology demonstration. It's a nice technology demonstration, but what's it actually used for? One of the things we did was we applied it to image classification. ImageNet is the largest computer vision benchmark in academia, and the task is to examine an image and decide which of 22,000 object classes the image is. It's a very difficult task. One of the tasks, or two of the categories, are stingrays versus manta rays. And the vision algorithm has to look at an image and decide if it's a stingray or a manta ray. And the other two classes are isosceles triangles versus equilateral triangles. I think that human performance on this data set, given how difficult and almost ambiguous a lot of examples are, I would guess human level performance on this might be around 30%. There's a gut feeling I'm about it on this essentially. This is very hard to do. So, previous are working on this, well, I guess with 20,000 classes, if you guess randomly, your accuracy is 0.05%. Previous state of the art was 9.5%. What we did was we learned the features from YouTube. So there are features from a ton of unlabeled YouTube video. We then took those features and combined it with a small amount of labeled data, like 20,000 object classes. And through that, our accuracy was 21%. Our research paper says 15.8%, which is one of those we covered in the book. This instead we report something 54 is substantial. And so this is a pretty significant improvement on computer vision. All this is now being rolled out across a number of other applications. So, before wrapping up, there's just one last piece that I want to talk about very quickly, which is the application of these ideas to natural language. And I guess I want to talk about that because I know there's a lot of research going on. And it turns out that there are some very interesting ideas on adapting these algorithms to language, which is one of the most important. So, the ideas here are a little bit different. Let's share a few points. So, before diving into how we apply deep learning to language, I want to just describe one idea, which is the idea of learning feature representations of words. So, given a word like Monday or a word like written, one way to represent the word is with this one on or one hot vector. You see this as a one position. But this isn't a great feature representation. So it turns out there's a literature on learning features for words. This is sometimes called distributional representations, other papers, various ways of doing this that I want to talk about. But the idea is, from each word, we're going to come up with a low-dimensional feature vector. So the word Monday might be represented by the feature 24 plotted over there, and the word written might be represented by the word 90. And with these algorithms, the word Tuesday will then be represented by a feature that's similar as Monday. This is what I want people to do, because Tuesday and Monday are kind of similar things. And the word France will be represented by feature vectors similar to written, and then on will be represented by feature vectors. So now, given a sentence that on Monday, written, blah, blah, we will represent the words using those feature vectors that we pull up from the top. So, I'm showing this with two-dimensional feature vectors, so I can plot it in practice. 100-dimensional feature vectors is more common. There are various ways, like LDA, LSI, LSA, distributional representation, neural language models, various ways to come up with these feature vectors. I don't want to talk about specific ways, I just want to know. Okay. So given a sentence like the cat sat on the mat, what we can do is pull up a feature representation for each of these words. Now imagine that you want to apply a deep learning algorithm to this, because the straightforward approach would be to stack on top of this a set of neurons to try to learn representations for different parts of the sentence. But now, if you look at that node, right, where the arrow is pointing, that node sees the three words cat sat on. So the job of that node in the network to learn a feature representation for the phrase cat sat on. But the phrase cat sat on doesn't mean anything, right? It's not a proper English phrase, so I don't know what it means to learn a feature representation for the phrase cat sat on. So for language, I think we should instead come up with an algorithm that respects the natural hierarchy that sentences come from. It's the pause tree structure. So in this sentence, the cat is a phrase, the mat is a phrase, on the mat is a phrase, and so on. And so if you look at that node, it's the job of that node, PP stands for prepositional phrase, which is the job of that node to learn a representation for the phrase on the mat. And on the mat, that is a proper English phrase. And we can think about how we can come up with software to learn a good representation, a good feature representation for the phrase on the mat. So, how would you represent the meaning of the phrase on the mat? We've been learning all about representations using feature vectors. We represent images as feature vectors, we represent audio as image features, we represent words with feature vectors, so we're going to represent phrases with feature vectors. And so the job of the algorithm is to come up with a feature vector, maybe A3 here, to represent the meaning of the phrase. So let me illustrate what we want. This is an illustration, so this is aspiration. This is what we'd like to do, not saying what we'd like to do is have an algorithm come up with a representation for the phrase, the day after my birthday. That is, let's say 3-5, that would that there. but it's pretty similar to Monday and Tuesday. And given a phrase like the country of my birth, you'll hopefully learn about future representation. And indeed, that would be close to Britain and France, because the country of my birth is something that's similar to Britain and France. So how do we do this? How do you come up with that mathematical? So I'm going to color in some of these ways just for the purpose of illustration. And the way we're going to learn these representations for phrases is we're going to use a neural network. So we're going to build a neural network that takes as input the two children nodes, so the THU and the A5. And it's the job of the neural network to output two things. First, it should output a yes or no to tell us whether or not those two children should have a common parent. In this case, the answer is yes. And those two nodes should have a common parent because that forms a valid phrase. And second, the neural network has to output a semantic representation, has to output a feature representation you want to use to represent this phrase. So, having trained this neural network, if you're given a new English sentence, you can apply the neural network here and ask, is the cat a phrase? The answer is yes. And the representation of the phrase the cat is maybe rectified to. Is cat sat a phrase in this class tree? The answer is no. Is sat on the phrase? No. No, and the mat is a phrase yes, and the representation of that phrase is THU. You can then build up the representations, one layer representation like so, and now you can apply your neural network. The cat sat is not a phrase, and so the sat on is not a complement is with representation THU, so you can now build up your representation and so on until you build a representation for all of the words in the class. I drew this illustration, I did this animation as though we make these decisions usually from the bottom up. For those of you that are familiar with pauses, you can actually use dynamic coding to find you can pop down the bottom up so the pause is So now what we have is for every word, every phrase, and for the entire sentence, we can come up with a feature vector to represent the semantics, the meaning of that English phrase. And so what we did was, to try to figure out if these representations are useful, what we did was we took a sentence, which we call the center sentence, and we computed the feature representation for this center sentence. Both took prefix yesterday. We computed the feature for that. And what we did was we looked through our corpus, looked through our set of English sentences, and we found the sentences with the closest feature with the most similar feature representation as the center sentence. And this on the right, the four feature vectors with the most similar feature representations. So the other things that most similar to both of Ferdinand's yesterday is we look for turbulence, so on. It thinks that Columbia, South Carolina is similar to unknown word California. Even though it's never seen this word before, it knows that unknown word California is probably a city in the United States, and is therefore similar to Columbia, South Carolina. Here are a few other examples. Pest and time to comment is similar to coastal with exclusive terms. These two phrases don't have a single word in common. We were lucky is similar to it was in the autumn. And so these are feature representations that are giving us a little semantics, certainly the syntax, but also a bit of the semantics or the meaning of these phrases. We did all this work in English. As far as I know, I'm not aware of anyone that has taken these ideas and applied them to Chinese yet, but I believe that all of these ideas will work well for learning semantic representations in Chinese as well. You can recursively build up feature representations for the meanings of different phrases, words, phrases, sentences in Chinese. But that would be something very interesting to talk about. What are these features good for? We apply these sentences, these feature representations, to a number of more semantics. So the paraphrase detection challenge is a problem in natural language processing where the goal is to look at two sentences and decide if the two sentences mean the same. They're paraphrases of each other. Over the last 10 years, natural language researchers have engineered a ton of different features. And with some amount of problem, setting down by using this representation to observe the features, we're able to immediately outperform all of the time engineering and natural language processing. We've actually applied this representation, so it's kind of natural language processing. Classification, sample classification, to basically truly intelligent machines. They can do a lot of the things that humans can do. You know, our progress has been very limited. So for most of my professional life, I was actually pretty down with the AI field. And as a Stanford professor, you know, if a Stanford freshman comes to me and says, oh, I want to work on a big AI field, or really intelligent machines, you know, I would say, well, and I wish I hadn't said that to the Stanford students now. And frankly, it was only about 5 years, it's about 6 years ago, learning about the latest results in neuroscience and seeing the latest results in machine learning, results like sparse coding and algorithms, this idea, the neural rewiring experiments, suggesting that maybe most of human perception may be a single learning algorithm. It was really seeing those ideas about 5-6 years ago that for the first time in my professional life, I felt like we might actually have a shift and making some progress towards the big AI. It's not going to be easy. We don't have the right algorithm yet. It's not going to be 1 or 2 years. It might be decades. But seeing some of the latest results in neuroscience and machine learning and the ability of our algorithms to do amazing things and then some companies great, I feel like we might have some progress over last month.